welcome to the Spring 2026 Physics Seminar Series. We have talks every Wednesday at 2 o'clock usually, but this semester is a little bit different as we are having candidates for condensed matter physics search. Some of them are coming on non-standard dates and times. And so please check the physics seminar page for all the seminar time slots for the semester. We are actually having the next physics seminar talk tomorrow at 2 o'clock in the room next door on condensed matter physics. Today, however, we are very pleased to have Warren Pickett visiting. And it's my pleasure to introduce today's distinguished speaker, Professor Warren E. Pickett from the University of California, Davis. Professor Pickett is a condensed matter physicist and materials theorist. He began his academic journey in his home state of Kansas by earning both a bachelor's and master's degrees from us at Wichita State University here, before pursuing doctoral studies in physics at Stony Brook University, where he completed his PhD in 1975, when I was 3 years old. Following his doctoral work, Professor Pickett enriched his scientific training with postdoctoral positions at the University of Bristol and as an IBM postdoctoral fellow at the University of California, Berkeley. He subsequently held research appointments at Northwestern University and then embarked on an 18-year-long career at the Naval Research Laboratory in Washington, D.C. And in 1997, Professor Pickett joined the faculty of the University of California, Davis, where he has served as professor of physics, later becoming distinguished professor and chair of the Department of Physics and Astronomy from 2008 to 2011. And over his career, he has been recognized as a fellow of the American Physical Society, the Institute of Physics in the United Kingdom, and the American Association for the Advancement of Science. Professor Pickett's research focuses on the theoretical underpinnings of quantum materials, from magnetic phenomena to the behavior of electrons in complex solids. Among his many impactful contributions are computational investigations of high-temperature superconductivity, advances in understanding half-metallic ferromagnetism, and predictive modeling of novel materials. His work continues to influence both fundamental science and the quest for practical superconducting materials. Please join me in welcoming distinguished Professor Warren E. Pickett as he presents the quest for room temperature superconductors.
Thank you for that introduction. And what that introduction proves is that Holger is very good at introducing speakers, right? Okay, the quest for high temperature superconductivity. Maybe not everybody here knows what superconductivity is. So let me draw something, a slide that I didn't present here, and I will refer to it later. It's a simple graph, temperature going this way, the resistivity that Camerling Onus was measuring of mercury. Resistivity is a function of temperature, and it was looking pretty normal down at, say, 8 degrees Kelvin. And at 4 degrees Kelvin, he was trying to liquefy helium in 1911. At 4 degrees Kelvin, the resistance just went to 0. And he measured a little bit lower and was getting 0, 0, 0. And he quite properly stated that actually he couldn't prove it 0, but the upper limit of the resistance here was really quite small, like the 10,000 before it was here, something like that. Okay, so that's the primary feature of a superconductor. There's a normal metal up here. And it's a superconductor down here with no resistance, which is fascinating and potentially important. My early slide will show this. And there's a magnetic effect also, which I will talk about. All right. So this quest for high temperature superconductivity, in 2005 at Notre Dame, there was this workshop that I went to, the possibility of room temperature superconductivity. And following that, it's a very good meeting, didn't solve any problems. Lots of ideas presented and discussed. And following this, I know of about 6 or 7 more workshops like this over the next decade. I went to 2 or 3 of them. One of them I went to was this one. And I don't have a nice looking poster here, couldn't find one. But this was in Leiden, right here, the Netherlands. And it was particularly interesting because I could look out the window across the street to see where the laboratory was that Camerling Onus first saw this curve 103 years earlier. It was actually a better workshop than the first one because there had been some developments to be discussed. All right. So this has been of great interest since the 1950s or 60s. Higher TC materials. They're of interest and potential importance for the electricity grid because about 8% of electric power that's produced is spent and wasted on transmission. About 8% because resistive wires produce heat, which wastes energy. All right. Now, sorry. This is a 200-ton superconducting magnet for fusion power for maybe 3 decades ago, something like that. But there are a lot of windings of superconducting wires in here, big coil, and lots of high current, and a very strong magnetic field in here, which combines a plasma in which they were trying to produce fusion power, not fission power, not a bomb, but fusion power, which would be very potent and very clean if it could be made to produce more energy out than energy in through fusion of nuclei. Well, MRI is something else. Magnetic resonance imaging machines. I've been in one of these 4 different times, I guess, in the last couple of decades. And about half of those these days are using superconducting windings to produce the magnetic field. The other half are using normal state wires, copper and whatever, which are cheaper to make, but more expensive to run. Once you have wiring in there that doesn't waste electricity, then it becomes cheaper to run in the long haul. Okay, the next slide is me, and this is a track of magnets, commercial one that my colleague Valentin Taufour bought. It's a demonstration, and his undergraduate student, Haley, helped with this demonstration. And what it is a row connection of magnets and a track here, circular track in this case, with all the north poles pointing the same direction. And that's, at this time, he was trying to make his own, and he said it's not easy to hold those bar magnets in place and glue them down, fix it down, whatever you want to do, because that's not a low energy situation. Magnets like to have south pole against north pole. But to do this, what the demonstration is if you take this piece of rather high temperature superconductor, it's an yttrium YCBO, yttrium calcium copper oxide material with becomes superconducting not at 4 degrees Kelvin here, as in mercury, there, but at 93 degrees Kelvin. Room temperature is 300 degrees Kelvin. We'll get to that. Okay. So you put this YBCO material into liquid nitrogen, which is a temperature of 77 Kelvin. It becomes superconducting. You stick it on this circular track of magnets, and it will be levitated above the magnets because the superconductor repels the magnetic field. The magnetic field pushes it up and has to push around it to produce the levitation. And okay, so this would get this started, then it would just run around by itself without any friction, except a little bit of air friction. And you could even turn it upside down. So I'm demonstrating that here, turn it upside down, and it doesn't fall off. So I'll say a little bit more about why that happens. Okay, so this is my two last students and postdocs, also at this demonstration right here. And so what I'd like to show you is something that's a little bit more impressive. So Hoger, I'm not sure with Windows how to go to the first video. Right. Okay, so I know how to start it, I think. So, all right, there's a little background music here. What this is that Lexus decided 2 decades ago or so that enough young people were buying their cars. So instead of lowering prices, they made this video. What Lexus did was to create this track, which is a skateboarding track, it looks like, but in fact, buried underneath the surface is a track about just a track about this wide, and you can't see it. They went to England and got a champion skateboard person to learn how to ride this thing, and it's superconducting. There's a track of magnets below, and you can see because there's no friction in skateboard, you have friction to work with. You have to things to learn. So he falls off many times, and this is mostly superconductor here, and it's still below 93 degrees Kelvin. So he's learning how to ride it now. The track goes under water here, and learns to ride it well enough to go across this track, around the track, and you'll see he even rides over a Lexus here in a moment. Okay, so here he's learned where the track is, and the skateboard certainly knows where the track is. Skateboard is going to follow the track because actually there's magnetic flux frozen in to the skateboard, which not only helps to keep it levitated, but keeps it on the track. And so this just goes 30 seconds more maybe, but here the Lexus comes into view, and it goes, and yes, flies right over the Lexus onto the rest of the track. And oops, something happened. What happened was that the superconductor warmed up and became a normal metal, and it doesn't float anymore on the track, and he felt the result of that. Okay, so that is Lexus's demonstration of superconducting levitation above a magnetic. Okay, back to the presentation now. Can you hear me better now? Okay, well, at least, somebody back there can scream louder, then that's okay. All right, so this is a graph of the superconducting discoveries over time, getting higher and higher. And here is mercury at 4 degrees Kelvin. You can see it's 4 degrees Kelvin, and it's 1911 when it's discovered. And here are other elementary metals with higher TC, but you can see it goes up to 1986, and it's only gained 20 degrees in 70 years. So it's very slow progress, and there's really a lot of work done in this here by materials physicist, materials chemist, materials scientist, making materials, trying to make better superconductors, and there was discouragement. In 1986, something else happened. This new class of materials based on copper and oxygen, they all have copper oxygen layers, were discovered. First discovered with the superconducting temperature. We call it TC, T sub C or TC. First of 30 degrees Kelvin, and then 93 degrees Kelvin. Here's the liquid nitrogen temperature at 77, 93 degrees Kelvin, and then up to 134. And under pressure, you get up a little higher here, and so forth. So I'm not going to be talking about those kinds of magnets. I will get to these up here in a moment. So there's been a lot of activity in the last 3 decades of higher temperature superconductors, but room temperature is way up here. We're getting close with these hydride superconductors, but not yet room temperature. We call these near room temperature superconductors. Compressed metal hydride. Okay. So I'm going to give you a background here of about a dozen slides of progress of the state of the system, the theory, and the experiment. So in 1935, the London brothers, who were working at Oxford University at the time, Fritz and Heinz, made a big development. It's a phenomenological theory, but they said, okay, we know that this is a superconducting material. Let's just assume that there's a superfluid density of some of the conducting electrons, call it N sub S, and that those conduct electricity without any resistance. So you have to modify Maxwell's equations for electricity and magnetism. And what they showed was that that assumption led to the fact that the superconductor will exclude a magnetic field. That's called the Meissner effect. It had been discovered experimentally only 2 or 3 years before this theory. So the experimental discovery prompted the theory to broaden itself and to explain these effects. Later, not long after this, Fritz London went to Duke University and spent his career there, and Heinz London went back to Europe, and he was an experimentalist, actually. Okay, Ginsburg and Landau. Ginsburg I met a few times. In 1950, while he was a graduate student of Landau, generalized Landau's theory of phase transitions, which involve the free energy functional here, and some constants and some calculus in here and so forth. I'm not going to try to explain this, but what it posited first was, again, a phenomenological theory, but that there is a complex superconducting order parameter, capital psi, in this equation right here, which is not a wave function of electrons. It's a wave function of the superconducting condensate, which is a certain density of electrons. And this is what gives rise to the magnetic field, called the magnetic vector potential, but it gives rise to the magnetic field B. And this describes the interaction between the magnetic field and the superconducting wave function. And that was a big breakthrough. There are 2 types of superconductors. The first type of superconductor just excludes the magnetic field until the field gets too strong, and then it just loses superconductivity. Type 2 is a different kind, and it's the most important because it's higher temperature superconductors. And here is what Abrikosov explained with his theory, solutions to the Ginsburg-Landau equations, was that in type 2 superconductors, if you increase the magnetic field above a lower critical field, H sub C1, lower critical field, then you don't destroy the superconductivity. What happens is the magnetic field starts coming in through the surfaces here in vortices and forms hexagonal lattices. Hexagonal lattices like this. This one's not a perfect lattice because of defects, but what we have here is magnetic field lines coming through this 2-dimensional superconductor. All this purple is still superconducting. Okay. It is the fact that these vortices thread through the superconductor that allows the demonstration, the Lexus demonstration of what happens there, because it's this that holds the skateboard, in that case, in place. It's a really strong interaction between the magnetic field and the superconductor. Now to come back to this slide, again, that's what I want to explain. The reason you can make the demonstration here with the superconductor underneath is that those vortices are frozen into the superconductor, and enough so that the force is stronger than gravity to pull it down. So you can make this go around like this. All right. So I had a high school student working in the group for a few months, Amber, and she made this little demonstration here of what can help you to try to understand what might be happening in a superconductor. It's the interaction of electrons, which are denoted by little red balls here, and the positive ions of the lattice, that make up a crystalline metal in this case. And what happens is that this is a classical picture. It's not exactly right, but what happens is an electron comes through this lattice, and because it's charged negatively, and these are positive ions, as it goes through, it pulls these ions in a little bit. Now it goes on and goes away because electrons move fast and ions move slow. And later, an electron comes around here and it sees the positive charge here. It has a negative charge, so it's attracted to this region. This produces an effective attraction between electron and electron. The normal interaction between two electrons is repulsive. It's called the Coulomb interaction. And what this does when you do the quantum mechanics is it binds electrons into pairs. And the quantum mechanical description is that electron comes on here with momentum p. It excites a quantized version of this motion of the lattice. It's called a phonon. It's a quantum of motion here, and proceeds here with a different momentum here that's taken up here, and then later reabsorbs it. This sort of a virtual transition, but it's real. And that's the main interaction, which changes the character of the electronic state. Okay, that's called the bubble diagram. Okay, get to the main development in the theory, and that was due to Bardeen, Cooper, and Schrieffer in 1957 in a paper of 30 pages and 275 numbered equations. And as a graduate student, I went through in detail of at least the first 30 pages here and filled in the missing parts between the equations that they provided, and convinced myself that they didn't make any algebra mistakes anyway. And what they found was that with their theory, they could extract an equation which would give the superconducting transition temperature in terms of a characteristic vibrational frequency of the ions and an effective pairing between the electrons, which needs to be attractive. And then if this is attractive enough, then the metal will become a superconducting at temperatures below Tc. All right. To increase Tc, you would like to both have omega larger and to have lambda larger if you study this equation. And that's not easy to achieve. Scientists have found out over decades that's not as easy to achieve, mainly because when you increase the effective vibrational frequency, this is likely to decrease. So that's something to be challenged. This is a simple picture of the electronic band structure in a metal. This is sort of one-dimensional here. This is the electron energy of a state with momentum Q, which is cut off here, or momentum P or K or whatever we want to call it. And this is a simple picture, the bottom of a band. Electrons are such that you can only put one in one state, then you have to go to the next higher state until you fill up all the states, take up all the states necessary to include all your electrons. Then that's the ground state of the system, and you have all of these states filled. And then there's this energy right here, which is called the Fermi energy, which is where everything in a metal happens. At very low temperature especially happens right around there. And don't pay any attention to this line up here. And in a semiconductor or an insulator, you don't have a continuous spectrum here. You have a gap. Forget about the blue for the moment. You have a gap. And what happens is this band gap opens up and achieves a maximum here and a minimum here. And this is the gap in an insulator or a semiconductor. In a superconductor, you have a gap like this, but it's very different. That much of it is the same. You have the gap here, but you have another branch of the state energies, which comes down here. Actually, the fraction of electron that goes in here goes to 0, so it comes down a little bit and it sort of peters out. And the same thing happens up here. That's an effect of this electron pairing the materials, and it's not easy to explain that in any more detail in a lecture like this. But that's a simple picture. Superconductor, this could be lead above 7 degrees Kelvin, and this could be lead below 7 degrees Kelvin. And the BCS theory explained about a dozen properties that had been measured of superconductors. It was amazing. And it's still the most widely used and referred to theory of superconductivity now. And within 2 or 3 years after 1957, even more properties were checked that were predicted by the theory, and thermal conductivity, ultrasonic attenuation, and so forth. Also, when you look close careful, you could see the superconducting transition temperature effect there. Okay, so this I just want to mention, in real materials, you have electron states in 3 dimensions, and this is just showing states along, say, for cubic material, along the x direction, along the sort of x equal y equal z direction, diagonal in momentum space, and so forth. And you have several bands. Everything interesting happens right here. That forms the surface in this space. And here's the surface for something I'll mention later, sulfur hydrogen 3. Very interesting looking surface. But it's not just looking at this. You don't learn that much about why it's superconducting. What you have to do, and I'm not going to go through this, in the theory is, and the computational theory is to describe this main interaction, that electron with momentum k and one with momentum k prime coming toward each other. This one emits this quantized phonon over here and scatters to k prime. This one absorbs it, scatters to k prime. That's the primary interaction in a superconductor. That's important here. That energy transfer, the momentum transfer k prime minus k is q. Well, you have to evaluate this matrix element. It's rather difficult to do it, but now we can do it just given positions of atoms in a crystal and what atoms are there. It's called first principles method. You don't need experimental information beyond that, and you can do all these calculations to treat this energy operator that's so central from quantum mechanics. Here's electrons, here's phonons, and here's electron-phonon interaction. And the phonons are changed also in this way. We don't need to go into that. Okay, so now I want to, this was predicted by Chan Sui's group in 2014, and don't pay too much to the details here. These are the bands in momentum space for these quantized phonons, not electrons, but phonons. And this is what we look at a lot. But the bottom line is that they predicted that under pressure of 200 gigapascals, I will describe that in the following slide. For this cubic sulfur hydrogen 3, the superconducting transition temperature should be 200 degrees Kelvin. And anyone, including me at that time, would look at this prediction, amazing prediction, and say, yeah, fat chance, right? Okay. Because it's so much of a breakthrough if it were to occur. Well, what one needs to do to study these metal hydrides under pressure is to study the effects of pressure. So I have one more MP4 file. And we can understand the effect of pressure here, not on a superconductor. This is Queen and David Bowie, Under Pressure, 1982 song. I'm going to have to stop this soon because it's 5 minutes long. I really hate to stop it in the middle, but I have to. Okay, under pressure. They describe about pressure here, but not physical pressure, but societal pressure, I think it was. Thanks a lot, Holger.
Of course, now I can't upload the YouTube video without copyright violation.
Okay, so we're back here. So we won't have to do that again. So pressure. Let's look at pressure. I used some newfangled software to produce this graph. Pressure is measured in pascals after a famous mathematician and physicist from two decades ago, two centuries ago. 1 Pascal is 1 Newton per square meter. The physics students know what this is. 1 Newton of force is equivalent to the force of gravity of one pound, a mass under the force of gravity. So it's a Newton per square meter, and that's a very small pressure. So if you increase that by 5 orders of magnitude, factor of 100,000, you get up to atmospheric pressure. That's the pressure of air in this room right now. Okay, and that's also called 1 bar, 1 atmosphere pressure, 1 bar. If you go up another factor of 1,000, you get up to 100 megapascal. Down here, 1 kilobar, you go up another factor of 1,000, you get up to 100 gigapascal. And now we're talking about the pressures that the experimentalists have to apply to have to produce these new superconductors that I'm going to say just a little bit more about. And so forth, you go up finally to 100 terapascal, which you need cannons. Cannons are something that to produce instantaneous pressures like that. But if you blow up this little region here between 100 gigapascal and 1 terapascal, the hydrogen 3 sulfur or sulfur hydrogen 3 that I showed you was predicted to superconduct at 200 degrees Kelvin, which is 2/3 of the way toward room temperature, under 160 gigapascal pressure. And 4 years later, 2 groups found that lanthanum hydrogen 10 at pressures of 190 gigapascal, or maybe a little more, would superconduct at 260 degrees Kelvin instead of 200 degrees Kelvin. Those are predictions. All right, so that gives you an idea of just how high these pressures are. This is somewhere, Earth's core pressure is up here, another factor of 2 or 3 higher. Okay, Yanming Ma in 2014 made a prediction of hydrogen 2 sulfur or sulfur 2 hydrogen And this is something that's easy to load in the pressure cells that I will show you in a moment, because that's rotten egg gas. It's compared to other things to put in a cell, it's easy to deal with. And what he showed computationally, just computationally, using this well-developed computational theory, that if you put the material under 130 gigapascal pressure, or 140, 150, 160, the stable crystal structure was very low symmetry. This is called P bar, 1 bar. There's only one symmetry operation in this crystal, very low symmetry. But at this pressure, there's a change, and a different crystal structure becomes favored energetically. And there is where he predicted, in this particular case, 80 degrees Kelvin superconductivity at 160 gigapascal, like that. And this has not been found. Okay, just show this. What is a little bit special, or more than a little bit special, about hydrogen, and that is if you just use quantum mechanics to calculate forces on on the ions, hydrogen, proton, and the ion sulfur in this case, and just do time step by time step updating of positions and velocities and so forth, and conserve energy, then you get what's called molecular dynamics. And what you can see here is a sulfur with the atomic weight of 32 is hardly moving. And that's what you normally see in these calculations. If you look at this kind of presentation, but what you see is the hydrogens are jumping all around. And that's just the reflection that they are such light materials. Their atomic weight is 1. It's the lightest possible of any nucleus. So it's interesting. We did this calculation. My postdoc, Antia Botani, did the calculation. We were collaborating with another friend in the computer science department, Francois Gigi, to produce this and to learn some things about the dynamics of this system. Okay, that was sulfur hydrogen 3. In 2019, I mentioned lanthanum hydrogen 10 was discovered. 2 different groups. One got 250 Kelvin, one got 260 Kelvin. We always sort of quote the highest temperature. This is almost 90% of the way to room temperature from 0. T equals 0. And then yttrium hydrogen 9 back at 250 again, right around freezing. No, a little bit below freezing here. A colder room in Kansas 2 weeks ago, something like that. Near room temperature. Okay, these are predicted computationally, and they were discovered then by high pressure experimental groups soon after. Here is how this is done briefly. Mikhail Ermitz, the leader of this group, one of the top 3 or 4 groups, if not the top at this time in high pressure physics, studying superconductors at least. And he measured, and it was posted on the archive December 2014, and then a little bit more complete paper was published in 2015. But his experimental work was going on at the same time as the theoretical work that I guess I'll show you on the next slide. Anyway, what is done is to use 2 tiny little diamonds like this. They are of such that if you were to drop them off your lab table onto this carpet, or it would be very hard to find. You could just, or I can just barely see them if you're pointed out where they are. So you try not to drop them. They have very flat facets right here, this side and this side. You put your sample in there. This is something like 100 microns dimension. 70 microns is the thickness of a human hair. So 100 microns, that's the size of the sample. That's tiny, but they can load the sample. Then this is a metal gasket which deforms under pressure and confines these to smaller and smaller volumes, higher and higher pressures. You twist down the screws to produce forces above and below. And the diamond anvil cell, so it's called, that encloses all this, looks like this, and it's roughly an inch in dimension. And if you want to crank this up to 200 gigapascal pressure and take it to a synchrotron, you could put it in your pocket and get on the plane. I don't think you put it in your pocket because there's a fair amount of energy stored in there, but you can, that's the size it is. All right, and here is what Hermitz's group measured, and hydrogen. This is in sulfur hydrogen 3, and measuring the onset of superconductivity of this sample at 185 Kelvin. A better sample was 200 Kelvin. And here is the resistance drop down to zero resistance, the superconductivity drop. And then replacing hydrogen with deuterium, which is still just one proton, but it has a neutron, so it's twice as heavy. And the vibrations are square root of 2 lower in energy. Then this follows the theory. There's this huge isotope effect in TC. And that verified, this verified it's superconductor, and this shift verified that it's being paired by the interaction with the vibration of the atoms in the crystal, and in particular, the hydrogen atoms here. And here's the demonstration of effectively zero pressure, zero resistance down here. Okay, as I was going 2 years ago to a workshop at the University of Maryland, a couple of days before, I wrote to Yanming Ma and asked him what metal hydrides under pressure he believed to be superconducting, his group and whatever, and evaluate the papers, the results, and so forth. And he gave me this list of 10. There are actually 8 with TC above 100 Kelvin and at high pressure. There are 2 down here that are 2 low temperature things. They have magnetic metal atoms in here, which causes a difference in TC, but he listed 8 of these for me and got the result back to me in 18 hours. So I could talk about it at the workshop. This is the same list over here. I just wanted to show you the crystal structure of lanthanum hydrogen 10. This is a unit cube in this cubic crystal. So the structure is just this repeated in every direction, okay? It's a beautiful crystal structure. In a 1 to 10 ratio, it's about the most beautiful crystal structure you could have. And it's lanthanum or yttrium metal atoms surrounded by these cages of hydrogen. And these are called clathrate structures. But all of these high temperature superconducting hydrides have simple structures. And that's something we like to think about and we don't quite understand, but there are several things we don't understand. Okay, again, I got out my software and I just plotted, there's no temperature here. There is temperature TC scale here and pressure scale here. You can see 100 gigapascal, 200 gigapascal, and those 8 follow right along here, except for this one cerium is out of place. And it looks like to get to a higher TC material up here, you just need to apply more pressure. It's not that simple. Well, the next thing that was discovered, which I will show you, I think in the next few graphs, was not along this line. And this is just a small set of data. So I didn't, I showed this partly to be sort of humorous and not to be something to take too seriously. Okay, so this block is lanthanum, scandium-2, hydrogen-24, which was posted on the archive again, October of last year, 298 Kelvin. That's the temperature right in this room, give or take, at a pressure of 260 gigapascal. As I showed in the previous group slide, this is significantly larger than the 200 or 180 or whatever of the other high TC metal hydride materials under pressure. But this is different samples or different runs. So it's repeatable, and these experiments at this high pressure, and often the diamonds break and you have to start over. So these are not exactly reproducible, but this is a very good indication that in many cases that they get 295 to 298 degree superconducting transition temperature. Again, nice, not cubic, it's hexagonal now, but a very simple crystal structure, which is easy to understand, easy to do the calculations for. And here is resistivity versus temperature. And it's often found that at these very high pressures, the TC drop is not sharp. And it's because these pressures, and there's actually pressure temperature cycling with temperatures produced up to almost 2000 centigrade. So there's a lot of chemistry goes on in preparing whatever happens. But as you apply a magnetic field, this critical temperature goes down, and this is just representative of what happens in a superconductor. Okay, so I believe, yeah, this is just showing optical micrographs, I guess you'd call them, of, because it's a diamond, you can see through it very easily with X-rays and also with visible light. And these are electrical contacts right in between there. So you put voltage across two contacts and measure current across the other two and so forth to learn about the resistivity behavior. So that's, again, another picture of this diamond and the cell. So let me conclude with a nod to the humanities, which to me seem to have a little connection here. This is a poem, Trainer the Druggist, by Edgar Lee Masters. I'll read it to you. Only the chemist can tell, and not always the chemist, what will result from compounding fluids or solids. And who can tell how men and women will interact on each other or what children will result? There were Benjamin Pantier and his wife, good in themselves, but evil toward each other. He oxygen, she hydrogen, their son, a devastating fire. I, Trainer, the druggist, a mixture of chemicals, died while making an experiment, lived unwedded. This is part of the Spoon River anthology of a few dozen poems like this, which he was finally sort of declared one of the American genius writers, poets, whatever. All of these are written by dead people, which makes it interesting. Well, I changed a couple of lines in here and said, he sulfur, she hydrogen, their son, a stupendous superconductor. Okay, so with that, I thank you for listening. I'll be happy to discuss these things with you. Thanks.
That was a really interesting talk. We have time for at least a couple of questions. Yeah.
There's already a lot of heat in there because they put the sample in there, compress it, and then they laser heat it to very high, good Velma, laser heat it to very high temperatures, cycle, pressure, temperature, monitoring the resistivity, usually just the resistivity to see if something interesting happens. So they're changing the temperature and therefore the amount of heat in there by a couple of orders of magnitude as they do all this. That answers. That's right. There are efforts now, I'm helping with one of these efforts, to try to retain some of these metal hydrides with TC, maybe 140 Kelvin or something like that, to room temperature. And no, when you release the pressure here, usually the sample comes apart. But anyway, you don't, so far, you don't retain the high TC. Yeah. Yes.
If these superconductors under high pressure, is this, at this point, more of a theoretical accomplishment, or is it at all practical? Is there a practical use of these pressures?
That's very simple to answer. No, it's not even close. The sample volume, I don't know in micrograms what it is. I could calculate it, but it's a very tiny sample, and it even limits the number of experiments you can do on it. You have to keep it compressed. And what a couple of groups have managed to do is to measure magnetization as a function of temperature and pressure. And so that gives you the magnetic susceptibility, and that actually tells you the final fact you need to know, that the magnetization I showed you and the resistivity don't prove that the Meissner effect is there. So only in 1 or 2 cases has a group done the work to be able to measure the magnetic susceptibility, which is the magnetization at rather low magnetic field, and to prove that the Meissner effect happens.
Are all of the applications right now with the superconductors, like with the MRI machines, and that are they all atmospheric pressure then?
They are all at atmospheric pressure. So, so Nick will know about one of the important applications of superconductor wires, and that is the means of doing the high energy experiments at CERN, because there are superconducting magnets, which are, I don't know, 25 feet long, and then they're connected in a tunnel that's 17 miles in circumference, something like that. So there's a lot of superconducting wire there. These wires again produce the magnetic fields that bend the particles as they go around at some fraction of the speed of light. Yeah.
As you described, these samples are currently extremely small, and that's because we need to apply the high pressure,
Right.
and that can only be done on a very small sample. If we didn't need the high pressure, would we be able to make wires out of these materials? What are their mechanical properties? How stable are they?
Good question. So the wires that are used commercially, like at CERN and so forth, are, I think, niobium titanium, which is a simple alloy, TC of around 10 degrees Kelvin. But it's easy to keep them down at 4 degrees Kelvin. It's easy, relatively cheap. If you go to these copper oxide materials, which superconduct at 80 Kelvin, 93 Kelvin, even 124 Kelvin, they all have these copper oxygen planes, plus some stuff in between 2, 3, 4 layers of these planes. And they are, their mechanical properties are described as ceramics. Okay, so they crack easily, break easily, and so forth. So there's been a lot of work trying to make cables of these where the high TC copper oxide materials are the superconductors. And because, well, what's done, what can be done, you can make cables out of these, and you can make cables, they've been demonstrated, I think, on demonstration projects of 2 or 3 kilometers long, carrying a high current density. But you have to have the superconductor in here, then you have to have layers of something to protect the superconductor, and then you have to have copper, so that in case, or silver, in case the superconductor goes normal, it doesn't just blow up, but the current is carried by the copper or the silver. And the cables are tapes like this, by this thick, but they have like 11 layers to produce something that might be used as a superconducting cable. Yeah, so it's expensive, and it's not yet practical. But Yes, Bill.
Not a great article, but I read it. This may sound kind of silly. In Science News, just a little tabloid.
Yes, yeah.
There were a couple of issues ago, they were talking about vent graphene.
Yes, oh, yes. Oh, yes, that's a big field, already 8 years or 10 years. It's called, well, what they take is two graphene layers, which is just copper, a layer of carbon. And you can peel off single layer by single layer. And a couple of physicists who first demonstrate that this was easy and you can measure lots of interesting properties, shared the Nobel Prize. So you can make this double layer rotated layers. And yeah, lots of experiments have been done there, and superconductivity has been found there at about 1/2 degree Kelvin. 1/2 degree Kelvin. So did you have another question related to the, yeah.
Actually, most of the MRI machines still run on helium, liquid helium.
Okay,
That means that there's still a lot of room to grow there.
right.
Hopefully we can get away. Helium is rare.
Helium-3 especially is rare. I think helium-4 is not so rare, but and I suppose either one can be used in cooling, but helium-3 is very important in laboratories, research laboratories, and it is the isotope that's rarest. Yeah.
So my question is the PCS theory.
Yeah.
So the PCS theory is still working with people, right? Which I know that
So yes, BCS theory still works very well. Actually, there's a strong coupled generalization of it, but it still beats what people call BCS theory. And it works very well for these metal hydrides. And when sulfur hydrogen 3 was discovered to be superconducting at 160 gigapascal and 200 Kelvin, I believed it immediately. And several theoreticians that really wanted higher temperature superconductivity for even a year or two after weren't quite sure they believed it. But the fact that it was predicted first by Chan Sui's group, they did the calculations as well as doing the experiments. Well, they did the experiments later, sorry, but they did the calculations and made a prediction before using BCS theory, and agreed extremely well with the experiment. Yeah, so the theory works very well. So that's not a problem. It's materials problem.
With that, let's thank Warren again for really interesting. He is going to be here for another couple of minutes before he needs to head to the airport. So if you do have any other questions, please come down. But
Sure.
Other than that, join us tomorrow for the next seminar. Thank you.
Okay.